All right, 10-1. It's actually 9-1. We got new books this year, and they changed the chapter numbers. So I try to catch everything, but I named the file right, but then I didn't change that. All right, anyway, it's infinite series. It's actually 9-1. Given an infinite sequence, then the infinite sum is, so the infinite sum is the sum of all of the terms. So which is an infinite series or a series. So a little bit, you already knew that. A series is a sequence of partial sums. Oh, a series is a sequence of partial sums. That's a little different way to think about it. A series creates a new sequence. The partial sums of the series form a sequence. So we have two things going on is what they're saying. First of all, we have the terms. And in order for an infinite series to converge, the terms better go down to 0. So the limit of the terms better be 0. The limit of the partial sums, now that can be pretty much anything. It can converge to a value, it could diverge, it could shoot off to infinity. I'm going to keep reading, then I'll do an example where I explain this in a much better way, in a more specific way, not generally speaking. So the partial sums of the series form a sequence. So the first partial sum is just the first term. Second partial sum is the first two terms added together. And that's of real numbers, each defined as a finite sum. If the sequence of partial sums has a limit, we say the series converges to that sum. So if the infinite series is adding up, getting closer and closer to 3, we say, well, it's converging to 3. Otherwise, we say the series diverges. In other words, it's shooting off to infinity. The sum of series, when it exists, is not the limit of the terms, but the limit of the partial sums. All right, now that's probably clear as mud. Let's clean it up a little bit. We have the sum from n equals 1 to infinity of 1 over 2n, which is 1 over 2. Plug 1 in, you get a half. Then you get a fourth, an eighth, a 16th, 32nd, 64th, and keep on going. Now we could talk about the terms. The limit as n approaches infinity of 1 over 2 to the n is equal to 0 because the denominator is winning the race to infinity. We need that to happen in order for the series to converge. That must happen. There's no negotiating that at all. That must happen. So we can look at the terms. Now let's look at the partial sums. 1/2, just the first term. S sub 2 is 1/2 plus 1/4. And that's 2/4 plus 1/4 is 3/4. And what they said in the previous page was, you're forming a new sequence of numbers. And now we get to see what the sequence of numbers is and see if we can tell what it's going to. So let's go a few more and see if we can tell. Let's take the previous one and add on an eighth. That's the next term. 6/8 plus 1/8 is 7/8. So S sub 4 is 7/8 plus 1/16. That's 14/16 plus 1/16 is 15/16. Do you see a pattern? Can you get the fifth term without actually doing the addition? What do you think it's going to be? 31 over 32, right? What's 31 over 32 really close to? It's close to 1. So the sequence of partial sums seems to be converging to 1. And that's actually what the series actually converges to. So S sub infinity, or just, we don't really usually write that, we say the sum is 1. The series is converging to 1. So these two pages are saying there's a limit of the terms and then there's a limit of the sum. And there are two different limits. How they're related to each other, though. If the terms are headed to 0, then this has a chance to converge. If it's not 0, it's headed to infinity, negative infinity, or it could be alternating signs. It could be 1, -1, 1, -1. So lots of bad things can happen when the terms aren't going to 0. Let's look at a geometric series. And the one we just looked at is geometric. I don't know what that meant. I guess I do now. It just hit me. A sub n is 1 over 2 to the n, but so what? The geometric series, you can start at 1, and it's a sub 1 times r to the n minus 1. We don't want to start multiplying until we get to the second term. Now you can change that to a 0 if you want, but then you don't need the minus 1. I want the first power to be 0 either way. So it doesn't matter if you start with 1 or 0, you just have to adjust it to get that first power to be 1. You can start with 105 if you want, but we usually start with 0 or 1. Now what if we listed all these out? Let's say, I think I picked that one. The series is the first term plus multiply by r, then multiply by r, then multiply by r, and keep on going. So if we wrote a bunch of them out, the very last one would be finally to the nth one, the very last one. Well, now if you took that and you multiplied by r, you would get a times r instead of ar squared, and you get all the same terms, except the last one would have one more r than this one does, if you multiplied it through. Now this line says, all right, we'll subtract these. What would you get if you subtracted these? You'd have this one that doesn't have an a here, and this one is actually right before this one. So you would subtract all of these, all of them would match up, even this one would match up, that'd be gone, it would minus with that, but then this one would be left over. And so you're really going 0 minus this one, gives you that negative right there. So multiply by r, do a little subtraction, and you're on this line right here. Now you can factor out an s sub n and divide by 1 over r. So we're at this point right here. Now we'll end up with a sum as long as we can get rid of this. I need to get rid of this right here. If I can get rid of that, then we have a sum. But the only way we're going to get rid of this is if r is between -1 and 1. Here's what I mean. Remember, this is going to infinity. So if you have 1/2 to infinity, 2's winning the race, isn't it? So that goes to 0. That piece goes to 0. But if you had 4/3 to infinity, something bigger than 1, now the top is winning the race to infinity, and that shoots off to infinity. So we're good. We have a sum as long as r is between -1 and 1. This goes away, and then you're left with the little equation that we have for an infinite sum of an infinite geometric series. But r must be between -1 and 1, or else you're going to get it negative infinity. Or positive infinity. I guess positive because we'd have that too. All right. You have this on the next page, right? I wanted one less, if I could get one less page, if I could get one less one on this sheet, I wouldn't have to have this last page. So I condensed it, but I had already printed all this. I wanted to get rid of this page. So I just moved it up, but I had already printed all this. Sorry, I messed all, there you go. I messed your notes up. So I bumped this up, but that's not on your sheet. So it's the next thing. Does this converge? Well, a sub 1 is 1/2, because when I plug 1 in, we get 1/2. And r is equal to 1/2, because we keep multiplying by 1/2 to get the next term. The absolute value of 1/2 is less than 1, so we say this converges by geometric series. Now, if you get this question right here, does this converge, to get full credit, this is what I'd want to see. You don't necessarily need to tell me that a sub 1 is 1/2. That has nothing to do with whether it's going to converge or not. So if you want full credit on a quiz or a test, that's what you would write. Anything short of that will not get you full credit. I want you to know how I grade this stuff. Did I make it clear? Anything short of that, if you just say converges, you don't get full credit by geometric series. Now, the reason we do that is because at the end of the chapter, we're going to have about 9 different tests that you have to know. P-series, ratio test, integral test, nth term test, geometric series test. There's a whole bunch of them. So I want to know how you know this converges. Now, right now, you only know one test. And you're like, well, why do I have to write that? Well, you got to think about at the end of the chapter, you're going to have to tell me how you know it converges. Geometric series, nth term test for divergence. Geometric series test. A geometric series is in the form, do you want to start with 0 or do you want to start with 1? You'll have to adjust the little formula there, or a sub n. The geometric series diverges if the absolute value of r is greater than or equal to 1. If what you're multiplying by is 1, So if you're going 4 plus 4 plus 4 plus 4, that's geometric. The r is 1, but you're headed off to infinity. That's not going to converge. If the absolute value of r is less than 1, the series converges to the sum, and it's a tiny little formula. Determine whether the following series converge or diverge. R is equal to, well, let's do this. I think this makes it a little more clear. You don't have to write this. I wouldn't look for this. But a sub 1, let's talk about it, though. A sub 1 is 3 halves. Now, I get several answers for this. What do you think the r is? What are we multiplying by? 1/2. Can you see how someone would easily answer 3 halves? Do you see how that would be an easy mistake? We're not multiplying by 3 halves. The terms go 3 halves, then 3/4, then 3/8, then 3/16. So the r is a half. Absolute value of 1/2 is less than 1, so this converges by geometric series. Now here's the difference. Here's the r is actually 3 halves here. So a sub 1 is 3 halves. And on this particular case, because everything's in parentheses, the r is 3 halves, which is greater than 1. So diverges by geometric series. It's still a geometric series, but it just happens to be shooting off to infinity. There's nothing wrong with that. It just doesn't converge to a value. I don't want you to think divergent is a bad thing. It's not. It just doesn't converge. That's it. The nth term test for divergence. Notice it says the nth term test for divergence, which means you can only prove divergence for this. You cannot prove convergence for it. And I'll show you why at the very end of this slide. If limit as n approaches infinity of a sub n does not equal 0, then the series diverges. What does that mean? Well, if we take this one way back here, I said the terms are headed to 0. If that doesn't happen, if the terms are not headed to 0, this series is headed to infinity. So it would have no chance of converging if the terms do not go to 0. Note, this does not say that if the limit as n approaches infinity of a sub n equals 0, then the series converges. This is not a convergence test, only a divergence test. This test can only be used to prove divergence. If the limit as n approaches infinity of a sub n equals 0, then this test doesn't tell us anything, and we need to use something else. So this one, letter A, we're going to take the limit as n approaches infinity of 2n plus 3 over 3n minus 5. And that's ending behavior talk, so it's 2/3. But that's not 0. So the terms are not headed to 0. Matter of fact, the farther you go, the more you're adding on just 2/3 and 2/3 and 2/3 and 2/3. Imagine adding on 2,000 over 3,000. That's very close to 2/3. So this is headed off to infinity. We can say diverges by nth term test. So that's why you have to tell me how you know it diverges. That could be diverges by geometric series test, which would be wrong. But now you have a couple choices. On B and C, whether I wrote this or the author did or whoever did, wanted to show you that this and this are pretty much the same thing because we're talking about how fast this stuff is going to infinity. And n factorial is a tie. The difference is the 2. So the limit as n approaches infinity of n factorial over 2n factorial plus 1 is equal to 1/2, which is not 0. The terms are not getting smaller. They're getting closer and closer to 1/2. But essentially, at the very end, you're adding on a half every time. That's headed off to infinity. Really slowly, but it's headed off to infinity. Diverges by nth term test. Now this last one is the same thing, but it's just showing that we're comparing rates of functions going to infinity. 3n, that's equal to 1. It's 1 times 3 to the n over 1 times 3 to the n. So the 3 to the n's are the ones that are heading to infinity, so we look at the coefficients, which is not 0. This is not trivial. That is showing me you know what the criteria is for the nth term test. You have to have does not equal 0. That's a big part of it. All right. Why do I sound like I'm so mad today? Diverges by nth term test. I guess this, when I get excited about something, you can kind of tell. Why am I excited about the nth term test? I don't know. I can't explain it. I just like it. D and E I put on here to show that if the nth term test gives you a value of 0, means nothing. It proves nothing. All right, here we go. We're going to go the limit as n approaches infinity of 1 over n is equal to 0. However, this one diverges by harmonic series. Now, when I officially talk about harmonic series, you got to act surprised, because it's like you know what you're getting for Christmas now. So I got a little ahead of the game. So when I cover this, you got to go, oh, wow, really? That's the rules. Limit as n approaches infinity of 1 over n squared is also equal to 0. So the terms for this, for D are headed to 0. The terms for E is headed to 0. And all that means is they have a chance to converge. What do we know if the power is bigger than 1? Converges, right? So this one is called the P series. We say P is equal to 2, and we say that is greater than 1, so we say converges by P series test. Now, I haven't officially talked about the P series test, so when I do, act surprised. Make me feel a little better. Kidding, of course. But we haven't officially covered that, and that's not really the point. I don't need you to know how it converges or diverges yet. All I need you to know is that if the nth term test gives you 0, it could still, we have an example where it diverges, we have an example where it converges. So we don't know anything. We use a different test. So you got to think, well, what's going to happen right before we take the test at the end of the chapter? You won't even consider that. You'll look at that and know that it's the harmonic series. You won't do that at all. You'll look at that and go, oh, that's a P series. That's the hope anyway. So you won't even, at the end of the chapter, you won't even consider this as an nth term. Now, when you look at this one, you go, oh, that's 2/3. That fails the nth term test. We love the nth term test because there's hardly any work to be done. Some of the other things that you're going to see maybe in your homework, I grabbed this example here. Write an expression for the nth term. So we're kind of going back to just what is the nth term of these. If we have 1, 1/3, 1/9, 1/27, 1 over 81, the nth term would be 1 over 3 to the n. Because it says we're starting with 0. So 3 to the 0, 3 to the first, 3 squared, 3 to the third, 3 to the fourth, and so on. So that's the kind of stuff that we're looking for here. Now in letter B, the first thing I notice is that it's alternating. Plus, minus, plus, minus, plus. So the first thing I'm going to write is -1. If I put -1 to the first, if I put -1 to the n, and I plug 1 into this, I get a negative, but I want it to be a positive. So you either got to write +1 or -1. Pick your favorite one. I usually put +1. Now it makes it start with a positive. And then it looks like this is over n. Over 1, then over 2, then over 3. This is the alternating harmonic series. This one actually converges. And we'll see later on in the year, in the chapter, that it converges by the alternating series test. So the harmonic series diverges. The alternating harmonic series converges. And if I remember right, it converges to, I mean, it's obvious when I say it, it converges to the natural log of 2. That's sarcasm. It's my use of sarcasm. It's not obvious at all. Letter C. This is actually geometric. And someone in first hour and second hour got this one. Does anyone know the nth term for this?
5 times 10 to the negative n.
Yes. But I'd rather write it like this. You just made the power negative, which is fine. It's the same thing. Yep. So 5 over 10 to the n. Because it's really, when you plug 0 in, it's to the first, so it's 5. Then if you plug 1 in, how do you say that number? 5 tenths, and then 5 100ths when you plug 2 in, 5 thousandths, and so on. Yep, very good. Excellent. Off to the side, I said, let's take letter A, which you won't do on your homework, and let's look at partial sums. The first sum is 1. Not much info on the first sum. Plus 1/3. And let's go plus, I'll keep going, plus 1/9. Plus 1/27. Plus 181. Do you get a sense of what it's approaching? Does it feel like it's approaching a number, and what do you think it is? Yes, and you think it's approaching probably 1.5. Now, we only did a few terms, and it already seems like it's approaching 1.5, and that's exactly what it's approaching. This happens to be geometric, where a sub 1 is 1, and r is 1/3. So the sum is 1 over 1 minus 1/3, which is 1 over 2/3, which is the reciprocal of 2/3, which is 3/2, and it is 1.5. So we have a formula to see what it converges to, but what if it was such a crazy what if it was such a crazy a sub n that you really didn't have a formula, or you really didn't want to come up with one? Well, you could throw this into a spreadsheet, look at the numbers, and decide fairly quickly what it's probably approaching. You could do 6,000 terms if you want on a computer pretty easily, just on a Microsoft spreadsheet. So this process has value when you're working with a very complicated a sub n. Now, the ones we work with in this entire chapter are fairly straightforward, even though when we throw factorials in there, it gets complicated. But anyway, it has merit. In exercise 3 through 6, tell whether the series is the same as this. So let's find out what this series is. If I plug 1 in, we get 1. Plug 2 in, we get this. We get minus 1/2. Plug 3 in, we get plus 1/4. How about we go one more? 1/4, and plug, let's see, 1, 2, 3, 4 in, we get minus 1/8. So the question is, if I change the 1 to a 0 and a n minus 1 to an n, do we get the same series? Plug 0 in, we get 1. That looks good so far. Let's do a few more to see if it's actually a yes. Plug 1 in, I get minus 1/2. 2 in, we get plus 1/4. And if I plug 3 in, I get minus 1/8. I don't know, I'm pretty convinced that this is a yes. I mean, we could go 20 more terms, but I think we got it. Now they said on number 6, what if I start with 1, but this is an alternating series? That's what this always tells me, that it's alternating. And it is, plus, minus, plus, minus. So far, I don't know, it looks pretty good. But if we plug a 1 in, we get a negative. And then 2 to the 0 is 1. So right away, I get a negative 1. So on the very first term, it's not the same. I mean, you can keep going, but it's not the same. It started out with the wrong sign. So we're close, but didn't happen. Tell whether the series converges or diverges. If the series converges, give its sum. You have to be able to recognize that this is a geometric series where a sub 1 is 1 and r is 1/5. That's what we're multiplying every time to get the next term. Now, the absolute value of 1/5 is less than 1. So this converges by geometric series. And I wrote too big. The sum is 1 over 1 minus 1/5. That's 1 over 4/5, so this converges to 5/4. This is not geometric, but I can see right away that this fails the nth term test, or passes, if you will. Limit as n approaches infinity of 3n minus 2 over 5n is equal to 3/5, which is not 0. So diverges by nth term test. You got to be able to recognize that, especially when we get to the end of the chapter and we got 7 other tests that we have to be able to recognize. And I'll be talking to you throughout the chapter on how you recognize each. What's the characteristic? Geometric. A sub 1 times n to the, a sub 1 times r to the n, because we're starting with 0. So a sub 1 is 3/2. R is 3/5. And the absolute value of 3/5 is less than 1. So we say converges by geometric series. And the sum is 1 over 1 minus 3/5, which is 1 over 2/5, which is 5/2. Oh, I messed that up, didn't I? A sub 1 is not 1. That's wrong. It's right if a sub 1 was 1, but it's not. Let's try that again. 3/2 over 1 minus 3/5. 3/2 over 2/5. So I'll take 3/2 and times 5/2, multiplied by the reciprocal. So the actual answer is 15/4. There we go. Went a little too fast. This is also geometric. R is 3/2, which is greater than 1, so diverges by geometric series. And we don't find the sum. Sum's infinity. It's infinite. And then on this one here, this is geometric. A sub 1 is 2. R is, well, what would R be on this one? What is it? Close. You're negative 1/10, right? Because it's alternating. So that's kind of tricky. But the absolute value of negative 1/10 is less than 1. That's where absolute value actually comes into play, when it's negative. So converges. By geometric series. The sum is, a sub 1 is 2 over 1 plus 1/10. Because it's really 1 minus negative 1/10. It's always minus. So 2 over 11/10, which if I multiply by the reciprocal, we get 20 over 11. So it's 20 divided by 11. That's what this is converging to. But look, 2 minus 0.2 plus 0.02 minus 0.002. There we go. So I'm pretty convinced I have the right sum. I don't know why that says it. So this is probably like a, I don't know. This is review. This is old stuff. Give it a try. Help each other out. Oh, that took a while. I gotta get going, right? We almost out of here? 1:33, I think. 2:20 dismissal. Yeah, 1:33. All right, we'll get going on this. This is the one that one's on the chart. And so P sub 6 is x minus x squared over 2 plus x to the third over 3, x to the fourth over 4, x to the fifth over 5, x to the sixth over 6. Now, you probably were going to develop it, I would imagine, because we haven't used this one very much. But if you know it, it goes very quickly. So then P sub 6 of 0.2 is equal to, let's finish it out, 0.2 minus point, or is it all plus? Oh, I can't remember now. Is it alternating? Okay, all right. I thought it was, but then I started doubting it. Squared divided by 2 plus 0.2 to the third divided by 3 minus 0.2 to the fourth divided by 4 plus 0.2 to the sixth divided by 6. Is that it? Oh, I missed it. No, I missed 5, didn't I? 5, and then minus 0.2 to the sixth divided by 6. All right. Well, let's see how close we were. Natural log of 1.2. Yeah, I feel pretty good about it. 0.18232. All right, there we go.